So can you see my screen?
Yes, I think it's all good.
Okay, excellent. So good morning, everyone. It is my great pleasure to moderate this session on artificial intelligence and digital twin in MRO. My name is Nico Avdelidis, and I'm a professor and the head of the Integrated Vehicle Health Management Center at Cranfield University. First of all, I would like to thank the organizers for this huge effort to have this important event under such awkward times for everyone. And secondly, and very importantly, I would like to introduce my fellow speakers, participants in this panel today. So we got Hobby Raberivello from BI Expertise in Quebec, Canada, Joao Raposo from Cranfield University, Harald Koppelkoren from Elias Solutions, and Jürgen Donders from Gordian Logistic Experts. So today's session is about using different kinds of advanced digital technologies such as artificial intelligence and digital twinning, tools that could be used to actually synchronize, monitor, and improve all processes related to aircraft MRO. So basically collected data from such operations dealing with MRO, such as inspections, repairs, and so on, could provide the foundation of actually building a database for future machine learning to automatically and increasingly accurately identify and as well as suggest solutions. Furthermore, the use of a digital twin enables the simulation of liabilities that may occur during the life of the aircraft, enabling actually monitoring and diagnosis. This makes it possible to make credible fly-no-fly decisions quickly, as well as provide maintenance services with valuable information, and try to lead to a potential prognostic health management strategy that could be formed. Okay. So, as we're an academic research institution, some time ago we got an interest from the industry to actually develop an autonomous NDT inspection system for inspecting aircraft wing panels within a factory line of an aircraft manufacturer. And we started developing such an approach in order to automate it and reduce the inspection time, but at the same time trying to get decision making within less time than the actual manual process. The actual manual process could take sometimes between 1 to 4 hours, depending on the difficulties that each panel had. And the initial result that we got from this automated introductory suggestion that we proved through this developed project was approximately around 15 minutes. Of course, there was the main challenge in such an approach, which was the collection of data containing actual defects within the factory line. But nonetheless, we managed to develop a random forest algorithm that was implemented on training a specific data set of images that helps in order with features such as training, color, and texture to get the result of an accuracy of 96%, which of course was not perfect, but it was a clear indication that such an approach might work. And the data set, of course, was limited, like I mentioned. And with a bigger data set, you can actually get a very highly percentage as a result, replacing this automated process through the inspection service. Of course, this UAV NDT inspection service, in relation with other kind of research areas, such as the structural health monitoring and sensor monitoring, and utilizing vehicle reasoning with artificial intelligence machine learning, are concept facilities and research areas that we work within the AVIATION Center, and together with new developments and facilities such as the Digital Aviation Research Technological Center that we have with its own hangar actually to accommodate aircraft. We're looking actually into using digital twins in order to create a digital model of the aircraft and continually update the performance model with feedback from real-life testing and operations. This way, it will enhance actually the management and operation of the aircraft. So the main areas that you see on the bottom right corner of the slide, starting from the NDT, developing with the autonomous systems into the hangar lab and using the advanced digital technologies of artificial intelligence and digital twinning, can actually lead to make fly, no-fly decisions for the actual aircraft. Of course, this is something really fit for the future as an innovative idea during COVID times, because it aims at ultra-low maintenance, increasing at the same time the autonomy and the AI decision making, reducing human operators in the field on actually making the inspections, at the same time reducing the operational costs, and above all, achieving this without minimizing the aircraft safety. So I've already mentioned how we started with these UAV NDT inspections, and currently we're developing a new system under a UK-Canada funded project called Multiact. So this is a project that it's actually aiming to develop a UAS for the accurate and fast identification and location of defects in aircraft structures by non-contact means using active thermography and artificial intelligence approaches. Within Cranfield, there are two centers, the Autonomous and Cyber-Physical Systems Center, as well as the AVIATION Center that participate, but there are several partners, as you can see from this slide. Some of these partners are industrial partners, and Hobby, who's part of this panel today from BAE Expertise, is one of the industrial partners and will explain more within the project.
Thank you, Nico. So yes, my name is Hobby Ubivula-Reberdil. I'm Chief Strategy Officer at BAE Expertise. And so we're an AI company. So we're kind of the more non-traditional actors of the sector. And as we are part of this project, we aim at developing with our partners a system, an autonomous system, as Nico mentioned, where, as you see here in the concept, you have an autonomous drone which is surveying the aircraft structure. So it's an autonomous drone system where the drones are equipped with heating sources for active thermography and thermal and HD cameras. And the autonomous drone is connected to a ground station on which machine learning models are running that are detecting in real time the defects that appear on the composite structure, whether on the surface or in the subsurface of the underlying layers of the structure. And this allows to identify, characterize the defects, and also to locate them on a 3D model. So this is where we integrate into the digital twin concept, given that from a maintenance perspective, if we're talking MRO, the digital twin being a replica of the structure, engineers will be able to locate the structure to see how it evolves in time and to assess, given the different conditions of the history of the aircraft and how its operations, to assess whether it can continue to fly or it needs repair. So this is from a maintenance approach. But if we go further in the digital twin perspective, in the design aspect, so in a more evolved, advanced aspect of a digital twin, engineers would then be later on able, with more data relating to the operation, environmental data relating to flight conditions, will be able to improve the design of aircrafts and simulate changes to assess when, so on predictive maintenance, when to make changes on the structure or on the design aspect, how they can change the design, simulate different types of changes, whether it be structural or aerodynamic changes, to then make the system evolve at first digitally, and then when they'll be able to select the best design for their structure, to then produce it and implement it in the real life structure. So this gives an overview of how the system works and how we are in the research and development in the MRO, but also how it can evolve later on with digital twins, more smarter digital twins. Thank you, Nico.
Thank you, Hobby.
Okay, thank you, Hobby. Speaking a bit about Cranfield University, Nico has spoken a bit about the projects that we have been developing, also Hobby and this Multiact, but speaking a bit about the future and what we envision or what we are working on. The projects that we are setting up or the ideas we are building, we are looking in the information life cycle in what concerns digital twins, from data acquisition, transforming this data into information, and in the end, what to do with that information. From the data acquisition, we now have a whole new range of sensors that we can use, from autonomous inspection that, for example, the ones we saw in the Multiact. There are other projects like Compinova where we have a different approach to multi-autonomous systems that can acquire data, inspection data. There are other things under research like sensing, self-sensing skin for aircraft structures with new materials, new capabilities. And once this data is gathered, it's something that we could not have some years ago, but once this data is gathered, we have to transform this data into information. Someone once said that data is boring. Information is the interesting part. So how to transform the data into information, that's the challenge. And we are working on it at AI level, at other levels, but how to transform that data into useful information and then to decide what to do with it. In that sense, if you could go on the next slide, Nico. In that sense, one of the things that we have at Cranfield University, there is an MSc in Applied Artificial Intelligence that we are aiming to bridge the knowledge gap between the machine intelligence and human wisdom. What is different bit of this MSc is that this is an MSc created by industry. So all individual research projects are based on topics suggested by the Industrial Advisory Board. And the objective here is to address real industry problems. So apply artificial intelligence to real problems. And from there, with bright minds, bright young people with bright ideas, to take the next step and take the next look at the next future that we can build, also on digital twins, and also on understanding how can we do with all the data that's now available, what are the potential, what is the different possibilities that we can do with it. I think.
Thank you, Nico. Could you put it in a presentation mode, please? Thank you. So, Ilias, we are not a research company. We provide software, we're a software house, and here you see the end-to-end process that is being supported by Ilias with all the modules. So on the bottom we see Ilias Guide and iHums, our own smart sensor, which has AI included. And we have Ilias Guide as a technician as a sensor, so a lot of data coming from there, but also external hubs systems and external sensor systems, like actually we just saw the way Hobie explained it. This information is going into our transaction system, so making sure that there's valid data going through the transaction and making sure that our logistics and our operations are visible. Then on the top, we see the decision support environment. Exactly as Joao was saying, data is boring, but having the data and having the coherent data is key to get to a precise decision. The better the data, the more complete the data, the more granular the data, the better the decisions will be. And if you make better and faster decisions, you will generate more value. In this case, a lot more flying hours for less money. So we see the arrow going up and down. So in the end, things happen on a singular aircraft or one engine or one component. For instance, the landing gear, all that information is going up, leading to decisions at the level of a fleet, or, and that's what the triangle basically indicates, you can have multiple organizations, for instance, from the perspective of an OEM, overlooking several fleets. And then going down again, getting that decision down to where does, for instance, a technician needs to make an action, or somebody at the supply chain. And Jürgen will talk more about that after this. In the end, there is a digital twin in real life as sustained, but that digital twin can be enhanced and enriched with all types of sensors and AI around the aircraft, but also around, for instance, ground support equipment, painting the picture more and more complete, as Hobie was saying. So maybe the next slide will show an example of an external HUMS system. We in Belgium we do the full Belgian forces with our system. And one of their fleets are the NH90, and the NH90 has a HUMS system on board called GLIMS, and Ilias imports all the data from GLIMS, making sure it's captured, but also making sure trend analysis can be done. But not only that, automatically work orders are generated, and that has then an impact on the full support chain. Also, when things are executed, work is executed, information is put back into GLIMS, talking to the air vehicle, and actually this led to Belgium being the first country reporting maintenance feedback to NHI, the overarching organization for the NH90, via an S5000F message, and we're pretty proud of that. So back to you, Nico.
Yeah, thank you. Then Jürgen Donders here. I'm from the company Gordian, and I'm going to tell something about how all this intelligent data that is transformed into information can be transferred to business advantages. What you see on the left is a typical example of what is done with spare parts inventories. When each airbase has airplanes, and there is some chance that parts are going to break and that aircraft would be grounded, then what we typically see in a network is that at least one part is kept in stock at each airbase, which means that leads to high local stocks, because all parts that can break down are in the local stocks. It means low central stock and thus a high network stock. So large inventory investments are required. But with intelligent data of all the artificial intelligence that comes from artificial intelligence systems, we would have time, we would have warnings about when a part will break down. So if you only have, for example, 3 days warning time within Europe, we could centralize all the stocks and make sure that when we get the message that in 3 days parts are going to fail, we have time enough to transport a part from the central warehouse somewhere in Europe down to the airbase where that part is required. So that means we are going to centralize stock more, and that means reducing local stocks and reduce the total stock in the network, meaning that we can save lots of investments in inventories. Next slide, Nico. We did some calculations on that in research project, and I'm going to show you how big the savings could be. For example, in this case, we look at a network with airplanes flying in Norway, Denmark, Netherlands, Italy, UK, Belgium. We got airplanes of the United States Air Force in Europe, and for example, Israel. And there we have numbers of airplanes that would be in those countries. They all have their local stocks, and they are supplied from a central warehouse somewhere in Europe, and broken parts will be repaired somewhere in a repair shop. To start with, we have a closed loop of repairable parts. Suppose they have a mean time to failures of 8,000 days. For the statistical guys, it's a Poisson distributed model. The repair lead time is 100 days, and there's an overall required service level of 95%. And when you calculate the number of required components in this complete network, we would calculate that there is a requirement of 17 components in the network. And that means one component at each local stock point and 9 parts in the central warehouse. And suppose these components have a price of $50,000, then you can imagine that's quite a large inventory investment. But if we have only 3 days warning time, only 8 components in the total network would be sufficient. And there is a smaller number required because we have this warning time. And that leads to, we have time to transport the parts, and there is reduced repair lead times because we have earlier, we know which shop replaceable units must be replaced. So there's a reduction in inspection time, and there is a shorter lead time of the required shop replaceable units. But what is very important is that the information that we get from artificial intelligence systems is very reliable. So only a false negative percentage, and that means a component that fails without receiving a warning on beforehand, then the possible gains are much smaller. So for future research is very important to improve the reliability of all this information that we get from artificial intelligence. And that brings me back to Nico.
Thank you very much, gentlemen, and thanks everybody for their attention. So I would like to open the discussion with a few questions towards the panel members, and I think my first question and topic for discussion would be: we all know that COVID has actually changed the way we do things and has greatly affected the transport and aviation sector. However, advanced digital technologies could help the sector. And do you think this is the case? And if so, how can we achieve this?
Maybe I can start.
Go on, Overhaul.
Yes. So yeah, obviously we as Ilias we focus primarily on the defense environment, which is different, but we do see the impact of digital solutions on, as I was just saying, more precise decisions. So I think the current situation has put a lot more pressure even on cost and being able to precisely plan when do we need what, and to get to that, you need your digital solutions. You need to know how your performance is impacted, the performance of the fleet is impacted by certain events. So the more you know, the more information you get, and the better the information is, you will be able to translate that into decisions that will lower the cost. And basically, Jürgen was saying that, or all of us were saying that, because getting the right information via AI in the beginning, and I love what you guys have done with drones and robots, and getting that information in a digital way will lead to better decision making, but also on the supply chain side. And there's a lot of money there.
Mm-hmm.
And if I can add on Harald's comments, I think what Harald and Jürgen have shown is that digital solution, technology, artificial intelligence can already help the aviation sector into improving, and beyond improving decision, there's also improving the efficiency of your whole organization. Technology can help you change your practices, especially artificial intelligence systems. If we look at the Multiact project that I presented earlier, it's a way for you to change your practices. For example, if we talk about inspection, here you go from a team of people who are doing the inspections in several days. So your asset, the aircraft, is immobilized during a certain time, which has a certain cost also for the company. And you go to an autonomous system of drone squadrons that are doing the inspections in a few minutes, as you mentioned earlier, Nico. And here you have, not only you have time efficiency, you have also cost reduction, very high cost reduction. And there's another aspect, because you have less people operating in heights, in potential dangerous areas, you are more safe in your operations. You are more efficient in your safety, since you only need one person to supervise the drones, just to make sure that the system is working correctly. They don't even need to operate the drones, since the drones are autonomous. So here you have very high efficiency gains that can help MROs in their operations, and further on help also the OEMs and airline operators in their everyday work.
No, I think I agree with you, Hobby. I mean, this time saving that you do with the autonomous inspections and the things that you achieve through the AI algorithms for the defect assessment of inspecting structures, like we do in Multiact, for instance, it's something that for sure, research-wise, as a research project, for sure it helps the aviation industry. However, do you think that we are at the level that both of such technologies, as it's artificial intelligence and digital twinning, are mature enough, and the reliability is good enough, both for research purposes but also for the industrial use, or we need further research developments?
I think, if I can say something, for research purposes, I think we are at the starting point, in a way that I think the capabilities, both hardware and software, are coming to a point where we can really progress a lot more with artificial intelligence, with digital twins, but picking back something of that you said regarding COVID-19 and regarding all this situation, this provides us with an opportunity, but also a risk. There is an opportunity now, because costs and finances of companies' finances are under a lot of pressure. So there is this opportunity to introduce more artificial intelligence, more additional instruments that can help MROs, that can help supply chains, that can help humans and then help companies to reduce their costs. But we cannot make that at the cost of reliability. There's always going to be a question of reliability within the artificial intelligence. And I think this is going to be the major challenge in the coming years. So the challenge is going to be how to address this. We have the tools. I think we have the data. We can already have numerous ways of getting the data. We have the computers to handle that data, but how do we handle the reliability? That we cannot only do with artificial intelligence. It's also at the political side of things. So I think we can start developing the digital twins. We are at the point of researching actually the concept of digital twins. We can already have some, I call it sort of partial digital twins in some components or systems regarding the aircrafts. not the full aircraft itself, but at some component level or system level, we can have digital twins, better predictive maintenance, better information, even real-time information. But now we have to tackle reliability and confidence. I think that's going to be the next challenge.
Thank you, Joao.
And so if I can add on Joao's comment there, reliability and the, digital twins as AI systems, as they get smarter, since the more we will get data, the more we will be able to add machine learning models on those digital twins, and the more they will get smarter, making them artificial intelligence systems per se, the more complex the notion of reliability will be. But in order to, resolve this issue of reliability, there is a need to have a continuous collaboration between research and technology companies, but also with the end users, because as long as the end users do not involve in those research are not involved in those research and development projects, we cannot assess. It's hard to assess the reliability of a system. So I think this is the one point that is really important if we want to go further into the application of AI systems in the industry, beyond the notion of the technological power of the machine learning systems. It's really the collaboration that is important to resolve this issue.
I fully agree. I think it's not only a challenge of the research side, but also the technology providers, companies, even certification agencies and the political side. So it needs to be a collaboration of all these areas.
Yes, I fully agree as well. We are involved in in an initiative together with DTU, the Tech University of Denmark, where somebody's doing a PhD on a program that we do for load indication on armored vehicles, but we do that with the Belgian Armed Forces. And one of the lessons learned we have is that we as the industry need to keep the project management to make sure that the science has added value, and the reliability in the end is tested in practice by the customer, and getting that feedback continuously, working together, doing it as a team, leads to a product that can be fielded. Because in the end, it's not about the science, but it's about the application of the science. That's where it really should be about.
Yeah,
Jürgen,
I think
you're also still there.
Yes, I am, but listening and discussion is going all right.
I think what Joao presented in his slide about the artificial intelligence MSc course with the industrial support and the strong industrial advisory board, and also Harold, what you mentioned about your collaboration with the university in Denmark. I mean, we in Cranfield and in my center, we also work closely with many industrial partners. We have funded PhD students from the industry, and I think this collaboration, working together, academia with industry on research projects, even if it's like a small research project like the individual research project that the MSc course has, as long as the idea and the need, not so much the idea, but the actual need comes from the industry itself, then I think academia and research organizations can help to speed up the process in order to achieve a better result and go into more reliable results, or at least try to prove ourselves that artificial intelligence is actually something, not just, not some dumb idea of using data, but how do you actually train the data and how do you actually use it just for the purposes of making an environment faster and easier to come up to a solution.
Yeah.
Sorry, please.
No, I just wanted to say that I fully agree, because as I showed in the overview of our product components, on the top there is defense capability management. Imagine you have the wealth of data of full fleets, multiple fleets, and all the people with their currency levels and through time. 25 years of data of anything that happened to anything, from the operation to the maintenance to the supply side. The wealth of data is enormous. That we create an environment, defense capability management, where we create, let's call them dashboards, just for the sake of it. Where people can be helped to look at that data in terms of information. But I'm convinced that if we look at AI and the power of AI, that we truly can bring the next best action to every individual from their perspective, from their role, of all those thousands of people that are working in an organization. So that's not AI at the level of capturing data at, for instance, an aircraft, but it's AI to help us learn to see, to help us learn to understand what is all the information, what's the wealth of information that's available, and how can we open up that treasure and actually see it.
Yes, also agree. It's the data cannot. We cannot only resume ourselves to capturing the data or acquiring the data. We have to create the application. What is it useful for? Transform it into information and make use of that information. And also, I think. On what Nico was saying, probably we are at that tipping point, and then science cannot be only researched for the sake of science. Artificial intelligence cannot only be researched just for the sake of science. No, it needs to have an application. Otherwise, it will become only a buzzword in the future. It's a nice buzzword, but yeah, what's the value in that? Probably we are now at that tipping point, and I truly believe that there is value in that. I've seen applications that can become effective and can be useful to companies, but yeah, it's artificial intelligence cannot become a buzzword, and we need to all be involved in that, in the creating the value for the artificial intelligence. I understand what you said, Harold, about having a project manager to really guide, or probably I would call it better, an innovation management to really guide the science towards an application.
Yeah.
Because this all turns around companies and also money. And in order for companies to survive, they need to make money, and we need to find better ways to be more efficient and be more effective.
And if I can add, I think a last comment perhaps on data, because we all insist that capturing data is really important to understand what is important in the value chain, what is our role, how is it important in the value chain, and how digital twins can help improve the efficiency of the whole value chain. However, I think it's important to be careful not to try to capture all the data that is possible to capture. What is important is what data is critical to be captured. Because, for example, if we think of digital twins and how they can evolve in the future, we can have digital twins that can reproduce not only the system as the aircraft, but also the whole environment. So we could simulate aircrafts that are flying into storms that cannot be reproduced in traditional simulations, or in wind tunnels. But the question is, would those data, what kind of value would those data really add first, but also, what is the investment that I need to put in order to have this power? Because if you want powerful models, if you want powerful digital twins, there is an investment cost there, and it is important that end users, OEMs, maintenance, MRO operators, be careful to really think about what is critical in the data that I need, and what kind of sensors, with whom would I ask or share data in order to build the optimal system, and not necessarily maximizing the system. as seeing technology, seeing AI and technology as a panacea to all my issues into managing my systems.
Fully agree. I think there's a trade-off between what you can do and how much it costs. And like Carl was saying, we need to focus on what is relevant.
Exactly.
Gentlemen, I think we're running out of time, actually. I think we only have like 1 or 2 minutes left for the session. So I just like to, well, 1 minute and 2 seconds, actually. So I just want to make one final comment from my side, talking about data. And it was mentioned that data is boring. It might be boring, but on the other hand, it's also knowledge. So the more data we have, the more knowledge we have. And as long as we find ways to use it through these digital tools, we can only, get a better result if it's like something to do with the MRO, or if it's something to do for the airworthiness of the aircraft, or it's something to do for any kind of operation.
Fully agree.
Okay. Well, thank you very much, everyone, for their participation. Once more, I would like to thank the organizers for having and hosting this meeting, and talk to you again soon.
Thank you very much. Thank you.
Thank you. Have a very nice day.
Thank you very much.
Thank you very
much.
much. Have a nice day.